system lab compares to, say, the locking lab.
Seems a bit more straightforward.
Good, good. Are you complete? Have you finished the lab where you're?
I just started yesterday, but I'm halfway. So.
Oh, okay, good. I guess that's good news for other people that are starting. Anybody finished it yet?
I have. I finished it.
And any nasty surprises, or it worked out reasonably well?
I think it worked out okay.
Okay,
Yeah.
good. Was it easier than the lock lab?
I think so, at least.
Okay, good. Well, hopefully it'll be the case for everybody else too. Let me get started. And the topic I want to talk about today is virtual memory for user applications. On sort of guided by this paper from '91 by Appel and Lee. And so the starting point basically is that, as you well know now, that OS kernels use virtual memory page tables in creative ways. You've seen that with the lazy allocation lab, the copy and write lab, as well as many other sort of features that implementation or aspects of the implementation in x86. So and basically the argument that the paper makes, the paper argues that the user application should actually benefit too, or should have the same powers. Or these user apps can use VM too. And really, what I mean with VM, of course, user applications running with virtual memory, but what I really mean with VM is that they would like to have the same mechanisms that the kernel has to its access in user application or in user mode. So, for example, being able to take page faults and then respond to those page faults. Be able to change the protection bits or the privilege levels in the page table. And so the paper argues this case by looking at a bunch of different applications. There are like 6 or 7 different types of applications, and maybe it will ask you, like, what was your sort of favorite application that you encountered in the paper? Anybody want to chime in and thought which were?
They can allow the user application to decide that a page is going to be, I guess, they change the access bits for some particular page.
Yeah, that's one of the mechanisms. I'm just curious, like, which applications, so they make the case with a bunch of different applications, correct? Like the garbage collector or concurrent garbage collector, and it had a couple other ones. I was just wondering which ones you thought were most interesting. So what other applications did they use, or did they use to make their case?
I thought the data compression application was pretty cool.
Yeah. Okay. Any others that people were compelled by?
I thought the sort of shared virtual memory between multiple different systems, that was pretty cool. I don't think I fully understood how it worked, but the general idea of using the protection bits to make sure that different machines are using that shared memory in the right way and protecting invariants makes sense.
Yeah, that's basically, it turns out that whole area developed in that one paper that originally described the SVM developed in a whole research area. Where people have all kinds of clever tricks to try to make that actually that scheme to fly. Any others? Because they go off and they do a couple other paper applications, and they basically argue that, if you look at all these different, quite different applications, like the shared virtual memory, the data compression, the garbage collector, very different in nature. But it turns out that, all of them actually rely on a small number of virtual memory primitives to actually make it work. And so the first question that sort of the paper addresses is like, okay, what should the primitives look like that user application needs if they want to implement one of those applications? And so let me talk a little bit about that first. What primitives? And so the ones the obvious one, of course, you need something of a primitive that's what I call trap, basically to allow a page fault that happens sort of inside the kernel to be propagated up to user space. And then in user space, a handler, can then deal with its page fault, and then of course return in the usual way back to the kernel, and then resume the instruction. So clearly, in a primitive like that is necessary, because otherwise you couldn't do anything in response to a page fault. The other primitive that they talk about is prot1, which decreases the accessibility of a page. They talk a lot about accessibility, and what do they mean with accessibility? Anybody?
Whether it's read, write,
Yeah.
or for user.
Yeah, so different ways in which you can decrease the accessibility. You go from a page that maybe has read and write, you go to just read only, or maybe you go from read only to actually have no access at all. They also propose that basically there should be one for each individual page. So that's prot1. There also should be one that actually you can do that the application can call for a collection of pages. And so basically prot_n boils down in principle to calling prot1 n times. But why do they argue that you should have actually a prot_n version of this primitive too?
Is it because actually it's more efficient because the overhead of protecting n pages is not much more than protecting one, because they talked about something like amortizing the work of
Yeah, you're absolutely right. So basically, if you do a prot_1, you have to change the page table bits and do some work. And then at the end of that prot_1, typically we want to have to flush the TOB. You may remember this from the x86 implementation. And flushing the TOB is expensive. And so it would be nice if you could amortize basically the flushing the TOB overall, the page table changes. And so basically prot_n boils down to n times changing page table bits plus one TOB flush. And if you did n times prot_1, you would have one page table switch plus, or one page table modification plus one TOB flush for each page. And so you can save the TOB flushes. Does that make sense? Okay. Then the primitive called unprotect, and basically this increases accessibility, as they call it. Basically meaning, if the page, for example, wasn't read-only access, now we're just going to promote it to actually have read and write access. And there are two other primitives they're mentioning. One is, a primitive to actually find out whether a page is dirty, and another primitive, map2, which allows an application to map a particular range twice in the same address space, but with different degrees of accessibility. And we'll see that showing up in a second. So if you look at these primitives, does x86 support any of these? For user level applications?
Not out of the box, but maybe the alarm handler that we implemented feels close.
Good. Keep the alarm handler in mind. That certainly feels very close, correct, to just related to the trap one. But other than that, x86 supports none of these, correct? x86 has a very minimal Unix interface and doesn't support any of the sort of more advanced virtual memory primitives, even though internally the kernel itself does have all the mechanism available, but it's just not exposed to user space in form of system calls. And so really what the paper is arguing is that any sort of good operating system should provide these primitives as a system call so the application can use them. So that naturally relates to the question like, okay, what's the scoop with Unix today? Are these available? And it turns out that basically, any sort of, if you look at a modern Unix, like say Linux, these primitives are there. Maybe not exactly in the same flavor as argued in the paper, but they are there. And you even saw it in the paper, correct? Some of the operating systems did have some version had a subset of them, but today they're basically sort of widely supported. So if you look at Unix today, let's see how they are instantiated. And so one of the first ones that's probably the most important one is something that's a system call called mmap. And that can be used to take some object and map it into the address space of the caller. So for example, if you want to map a file, then the system calls something of this following form. You call mmap. Mmap actually has quite a sort of a bewildering number of arguments. The first basically says like whether you can specify a particular address where you would like that to be mapped to, or you can let the kernel decide to choose the address. And in that case, you specify just null, and the kernel will pick an address where to map the object. You specify the length. You specify the protection bits. For example, read/write. And then some argument I don't really want to talk about, but there's something called like map private. Basically, you have to say something about how what happens if you actually write to that particular object. But we'll skip that mostly. And then you can actually pass in the file descriptor and an offset. And basically what this says is that you should map the content of the file object pointed to by the file descriptor, and you take the file content of that object at offset and map that basically that particular address at a particular address with that length. And so this basically allows you to sort of what is called memory map a file. So you can basically bring the contents of the file into your address space with actually having to call read and write system calls. And it's sort of convenient, correct? Because then you can manipulate the file just with ordinary pointers. You can write at particular locations, and then at some point you can write the content back to the disk. And so this is a convenient interface to manipulate data structures that might be stored in a file. And in fact, you will be implementing this specific version of mmap, or some version, the file-based mmap, actually in the next lab. So this basically integrates, the file system part of x86, the virtual memory part of x86, and you get sort of hooked them up, and by actually implementing mmap. Mmap can also be used in other ways. So you can use the map a file. You can also use it to map anonymous memory. And that's basically sort of an alternative to SBreak, where basically you can sort of ask, the kernel, please, give me a bunch of memory and map it at this particular address. So that is one of the core system calls, and we'll relate it back to the primitives in a second. Okay, there's a couple more calls that are necessary to actually support the primitives that the paper argues for. And Unix has them, so there's more Unix today. There's an mprotect system call. So once you have something mapped into the address space, you can actually change the permissions. So whatever, you can make it just and protect a particular, so you map something in the address space, then you call and protect, for example, for a subset of that part or all of it, and map it at a particular protection level. And so, for example, if you did this, basically, loads could be executed, but stores would change into a page fault. And similarly, if you want to make sure that a range in the address space is completely inaccessible, no, you can and protect it with none, and basically then both everything, basically any access to that particular page or to do that address range, starting from address to address plus ling, will result in a page fault. There's a similar, there's a corresponding call to nmap called unmap that allows you to basically remove a mapping or move an address range. And actually, if you're curious, exactly how these calls work, you should look up the man page of these system calls. And then finally, the one that we really need is a system called SIGAction. And basically, this is a signal handler. And it allows the application to say, like, if a particular signal happens, then, call this particular function. And so you can install basically function F as the signal handler for a particular signal. And in the case of page faults, the signal that is generated is something that's called segfault. And typically, you might have seen segfaults in user code before. Typically what happens in the segfault is basically the application stops and crashes. But if the application had installed a handler for a segfault event or a segfault signal, then instead of the application being stopped, the handler would be called by the kernel, and then the application can maybe respond to that particular segfault in the same way, in some sense, that the kernel responds to a page fault and maybe fixes up the page table so that the execution can continue. And in this case, maybe the handler will actually call and protect or and change the permissions so that actually the instruction can be resumed and continue. And so in this respect, if you were the most familiar version that the thing that we have seen like a SIGAction was like SIGAlarm, as Amir mentioned a little bit earlier, in the SIGAlarm lab, where you could install the alarm program basically installed a handler that would have to be called at every clock tick or every period of time. And basically SIGAction is sort of the equivalent of that, but the general version of it, where it basically can respond to different types of signals. Any questions about this?
It seems like mprotect implies that you can add different permission levels on individual addresses, whereas in like XV6 that we've been working with, you can only apply permissions on full pages. Is that a difference that's present?
No, it's not a real difference. It works at the page level granularity. And it doesn't expose, there's a separate call to find out what the page size is if you're actually curious about it.
Thank you.
So if we think about these the primitives that were in the paper, we can sort of map them correct to like what currently Unix or what Unix typically provides. So what equivalent correct of trap that we're in Unix would be provided is something called the SIGAction call. Right. And about prod n and prod 1. What is the equivalent for that? Okay, so basically all three of them, correct? Basically, or it can be implemented using mprotect. And mprotect, is flexible enough that you could do it by single page, as just asked, or you can actually provide something that consists of multiple pages, and then you could do you get the same benefit of like one TOB flush for changing the permissions on a whole series of pages. Okay. These calls sort of almost directly map into some of the primitives. turns out that, dirty actually is a little bit harder to do. There's not a direct primitive for or system call for, although you can sort of more or less get it done with some tricks. And I'll talk a little bit later about map2. There's also not a sort of, there's a way to do it, but it's not completely, sort of as a system call that just directly maps onto map2. It turns out that if you, with multiple maps, you can actually achieve this particular functionality too. Okay, so one way to think about this paper is that kernel developers, maybe not totally driven by this paper, but kernel developers, have extended these or have provided these primitives actually to today's user applications. Okay, I want to say a few words about the implementation, just much more at the sketch level, and then talk a little bit about the applications themselves, and see how they use these particular primitives. Okay, so let's talk about, there's two aspects that are sort of interesting. One is actually what actually happens, inside the virtual memory system to actually support this. I'm just going to sketch this out, like what the most important pieces are. And in fact, this is sort of a little bit relevant to the Nmap lab that is coming up, because you're going to do something similar. So an address space typically in the Unix today is represented by, of course, the hardware page table, which contains the translations. But typically it's augmented with a set of sort of OS data structures, not unrelated to any specific hardware design. And these are called virtual memory areas, or in short, VMAs. And basically what a VMA represents is, you record some information about a contiguous range of addresses. So if you think about an address space, it might have number of sections in the address space, each forming sort of a contiguous range, and basically for each section there would be a VMA. And the VMA basically says, the VMA also has all the same permissions. So all the pages in that range have the same permissions, and they're backed, by the same object. So for example, if you have an mmapped file, then there would be VMA for that file that describes, whatever the permissions for the file, as well as the information about the file itself. The file descriptor, for example, that goes along with that particular VMA, and the offset in the file where that VMA corresponds to. And in fact, in the upcoming lab, you will implement a very simple version of VMAs and use that to actually implement the Nmap system call for files, where basically you can record in the VMA, literally the file descriptor and the offset that corresponds to that particular Nmap call, or the range that is being mapped. Any questions about this? Okay, so then the second piece, the sort of important, and we have a little bit of experience with, but it's probably worthwhile, going through, is actually how trap or sick action, or actually the handler, how an actual trap will work. Actually, be a little bit more careful. So how user level traps are implemented. And this follows very much the same outline as actually the SIG alarm system call, and then the up call that happened when a clock tick actually passed the time limit. And so the sort of setting here is not clock ticks, but page tables. So let's assume there are some PTE that has that's marked either invalid, or maybe it's like read only and you actually store to it. And so what happens when the application accesses that PTE that actually is basically invalid or doesn't result in a valid translation? Well, as then the CPU jumps into kernel mode, jumps into the kernel at a fixed address. You have looked at the trampoline code. The kernel saves state. So for example, saves the trap frame. And then basically asks the VM system, what now? What to do? And the VM system actually might do something. So for example, in the case of like this happened in the lazy lab and in the copy on write lab, where the trap handler code sort of looks at the page table data structures, and in this case presumably it will look at the VMAs and see what the scoop is for the address that where the processor faulted on, and see what needs to be done. And so for example, if it is a sec fault and the application had installed a handler to deal with it, then basically that upcall or the handler of the event would be propagated to user space. And so basically, let's say there was a handler installed, then basically we're going to get an upcall into user space in the same way as in the sick alarm lab. That will run the handler in user space. The handler might call for nprotect to change the protections, and then the handler returns to kernel code. There's the kernel, and then the kernel basically resumes the interrupted process. Okay, and when the kernel resumes that interrupted process, if, for example, the handler fixed up sort of the address space of the user program, then the instruction might just execute correctly. Or if something is wrong, maybe trap back into the kernel right away again if the hardware still can't translate that particular virtual address. Does this make sense? Maybe there's remember again the sick alarm lab, and then this should be quite familiar.
Yeah, I have a question.
Yeah.
What kind of, I think when we're allowing the user to effectively run handler code on a page fault, aren't there additional like security vulnerabilities that could result as a part of this? So I was wondering if you could speak to that.
Yeah, that's a great question. By the way, can maybe everybody turn on their cameras just to, if possible, if you're comfortable doing that, I really appreciate it. I think many students in the class will appreciate it too. Yeah, so is there a security issue? In the first, what do people think? Does this break user kernel or the isolation between different processes? Another way of asking that question: did sick alarm break the isolation?
Wouldn't it be okay because the that code, that the handler would still have access to the same virtual memory? I mean, if there are different virtual memories for the process and for each of the processes, then that handler shouldn't be able to look into other processes' memory. So
Yeah,
it should be okay.
Yeah, so when we do the upcall, correct, we make the upcall in that specific user space that actually installed the handler. So the handler basically runs in the same context as runs with the same page table as the application that installed the handler. And so the only thing it really can do is, affect that application. But, that is the application problem. It can't really affect anybody, any other application, because it doesn't have any access to the other application's page tables, or can force a switch into them. So this turns out to be fine. Of course, if the handler doesn't return or does something bad, in the end, the kernel will just can always kill the process. So nothing really, the only thing that can go bad is, the process can hurt itself, but it can't hurt any other processes. Amir, does that make sense?
Yes, thank you.
Okay, so now I want to go through a couple examples, and sort of see how you could use it. And I'll start out with a very simple example to get ourselves into it, and then we'll move to the garbage collector, because lots of people ask questions about the garbage collector. So that seems like a good one to dive into. Okay, so the first example I want to talk about is a trivial idea, but in fact, it's not even mentioned in the paper. But it is sort of a cool way of illustrating, the power that applications get if they actually have these primitives available to them. And the basic idea is to actually build a huge, memorization table. And the memorization table is basically what it does. It just remembers, the result of some computation. And so, for example, you can think about it in the following way. Let's say here's our table, and the table starts at whatever 0 to some n, and what the table stores is the result of running some expensive function for that argument 0, or for whatever fn. Right? And so, if you wanted to, if this table was sort of pre-computed, once in the beginning of time, and then you wanted to look up, you wanted to know what the value for fi was, well, what you just do is you just look up in the table, in the slot I, and basically you get the value that fi would have computed. And so basically you turn maybe an expensive computation, maybe f is very expensive, into basically a table lookup. And sort of a cool trick, to basically store the results of pre-computers and store the results of an expensive computation. And if that same computation is executed many, many times, then pre-computing it once might be an advantage, a smart thing to do. Does that setup make sense? Okay, so then the issue, of course, is that the table, or the challenge, the table might be big. It might be actually, in fact, very big. It might be bigger than basically your physical memory. But it's still nice to have it. And so the solution, one solution, that you could use to solve this problem is to basically use the virtual memory primitives, as described in the paper. Primitives. And what you do is, first of all, you allocate a huge range. But don't really map, don't actually allocate any physical memory corresponding to that range. Just take a huge part of your address space and say, I'm going to use that part of my address space to actually store the table. And then so the page there's no content in the table, because the address ranges exist. And so if you do a table lookup for a table I, that will result into a page fault. And so the basic plan then is, on the page fault, you compute all the entries, or all the page basically covers a bunch of entries in the table, and for each one of them, you basically you compute the function fi and store it in the slot table I, and then basically resume the application. Right? And now of course, and map the physical page. So basically, you take the page fault, you allocate a page, and basically store in that page the results of fi for all the slots in the page. And the advantage of it is correct. If you now, a couple of advantages of, if you have to ever, compute fi again, you're going to actually do the table lookup, and you don't actually have to do any expensive computation, just the table lookup. And in fact, even if you do table I plus one, like, there's presumably going to be a bunch of entries in that particular page. They're all basically going to now be free, just table lookups. Of course, if you keep doing this, then you're going to consume all physical memory. And so, the page fault handler also, has to throw out some pages if, you're running out of memory. So if, much memory is in use, free some of them, free some pages. And of course, then you have to change the protection level, correct? To make sure that you're going to get in the future a page fault for those entries. So you have to presumably call prot 1 or prot n to reduce the accessibility of the page in the terminology of the paper. Does this make sense? As sort of a plan? Any
Oh,
questions
sorry,
about that?
Ben.
Sorry?
Yeah, you would need to map it. It would need to request from the operating system to map it to a particular address, right? Because it can be anywhere. Okay.
Yeah, or it could be anywhere as long as the operating system tells where it actually is. So
Oh,
maybe,
okay. I see.
maybe to make it a little bit more concrete, actually, I have a little implementation of this plan, and we can just look at it and see whether how you actually do that using the existing the Unix primitives. Let me, okay. Can everybody see the Emacs buffer? Is the font large enough? I assume that is a yes. So here's the application. Let me go to the bottom. So here's main. Main basically sets up the square root region, basically allocates address space, but doesn't really allocate the physical pages belonging to it. And then it calls this function test square root region that basically goes through that table in sort of a random order and basically checks whether the square root entry in the table for that position is indeed the correct square root value by just computing it literally before that. Okay, so basically the test square root region is going to run and it's going to presumably generate page faults because none of the table is actually filled in so far. So how does it, how do we get those page faults? Well, here's the sort of the fragment of code that you need to basically install a handler, a signal handler for a particular event. We're basically saying here, install for SIG, the SIG-SEC-V event, the handler SIG-SEC-V. And so when a sec fault happens or a page fault happens, then basically the function, the kernel will call handle SIG-SEC-V. And basically you can extract, the faulting address. This looks very similar to your sort of trap code that you've seen many, many times before. And basically the plan is very straightforward. We map a page at that particular address, so because that's the address that we want to fill in with, so my expansion function here, or the replacement for the expansion function, or the role of the expansion function is the square root function. And so we want to basically fill in, the square root of whatever value has to be there at that particular location in the table. So we allocate a page and map it there. And then, we calculate for that page all the square root entries, and then we're done. And this application is a little bit extreme. What I did is basically I run this table with only one physical page allocated. So whatever the last page was, we just release it by unmapping it. And so we have a gigantic table that's basically represented by one physical page. And we can just run, if we wanted to, we could run this application, but it's not going to be that particularly exciting. But why not? So I think I've compiled it, and basically goes through and just randomly bounces around in that table, presumably, causing a lot of different page faults, and all the entries, actually work out. And so even though there's this gigantic, square root page table or virtual square root table, the actually physical representation of that table just consists of a single page. And this sort of an example of like one of the, very simple example of one of the sort of cool things you can do if these virtual memory primitives are available to user applications. Any questions about this?
Could you just quickly go over that last point on why there's only one physical page? Because I guess I was thinking like during it, like, oh, like this sounds similar to like lazy allocation. Why is it different? And I think that like answered my question, but I didn't quite follow why we ended up with one physical.
Okay, the reason, okay, so when we set it up, we have no pages. So the set of square root region actually allocates address space, but then unmaps all the physical memory associated with that address immediately. So at the point of startup, there's no physical pages allocated to this particular table. Does that make sense?
Yeah.
Okay, then when we get a page fault, that means there's like one page out of the whole table that we have not mapped, and we have mapped no pages, but we're going to page fault, and now we're going to map one page. And in that one page, we're going to fill in whatever, the square root of I plus one, I plus whatever, just, for that particular page. And then if we had a page mapped, which in this case, the first time around we didn't, there's nothing to be done. So now, the application runs, and looks up some more entries in the page, in the square root table, and we get another page table, another page fault, because it's looking up a square root entry that actually was not on the allocated page. Okay. So at that point, we get another page fault, and then we allocate a second page. We calculate the square roots, for that particular page, and then we unmap the last page. And this is, of course, like in practice, you would never do this. Right? In practice, you would try to keep like a working set of pages or something like that. But just to show that you can go pretty extreme, that you can represent like this huge page, this huge table with a single page of memory, this particular fragment of code unmaps the one but last page. And then it keeps running. And so at any point in instance, at any point in time, there's only one physical page being used. Does that answer your question?
Yeah, I think so. Thank you.
Okay, good. It's just like it's more like, this is clearly not something you would do in practice, but it is more sort of like to show, the power of the primitives, that you can represent, this gigantic table using one single physical page. Any other questions? Okay. What I would like to do next then is talk about another example. And in particular, I want to talk about the garbage collector. Since a lot of questions were about the garbage collector. And so the idea, garbage collectors are a way of basically for programming languages or languages that basically do memory allocation and freeing on behalf of the programmer. So the programmer doesn't have to call, like in C, correct? You have to call malloc, and then you have to call free explicitly to free the memory. Languages that use garbage collectors, basically the application only has can call malloc, but never has to worry about actually freeing the memory. Basically, the garbage collector will do the work to determine if the memory still is in use, and if the memory is not in use, then it actually will free it. And so it's nice. What are some example programming languages that have garbage collectors?
Java.
Yeah, Java, Python,
Go.
Go, many of them actually, correct? Almost, other than maybe C and Rust, every other programming language basically has a garbage collector. Okay, and so as you can imagine, there's a huge literature and design space for garbage collectors. And the point of this paper is not like to say, well, here's the best garbage collector possible, but here basically illustrate that garbage collectors could take advantage of these user level virtual memory primitives. And so the particular garbage collector the paper discusses is a copying garbage collector. And the basic plan is sort of, the top level outline is as follows. You basically have a memory, a heap from which, memory is allocated. You divide the memory, the heap in two pieces. One is the from piece, or what the paper calls the from space, and the other is the to space. And let's say we're having started, with the application just starts, and so all memory is free. You basically start allocating memory in the from space. So like say we allocate maybe a tree-like data structure, that has here's the root of the tree, and that maybe has a pointer, to another object, and that maybe has a pointer to another object, and that is also pointed to by the root. Sort of a little cycle of objects. And maybe the application used a lot of other memory too, but there's nothing pointing to it anymore. And so basically the only objects, live objects, are the ones that actually are basically accessible from the root. So at some point, like maybe I've allocated lots of memory before, and we allocate one more object, and it turns out there's no space anymore, or the application asks for one more object, and it turns out there's no space anymore for it because the whole from space is basically has been used. And so then the basic idea is in this copy and garbage collector is to take the objects and copy them over to the user to the to space. And the way you do it is you start from the root, because that so every application or every has a set of registers, where basically the top level pointers are stored, or maybe they're the local variables on the stack. And basically there's a set of roots, and just for simplicity, I'm just going to assume there's one root, and you start tracing basically from the top level. And so, you copy the root object over, to the to space, and that's the only thing you do at that point. And then, of course, that leaves, the pointers, still pointing to whatever objects there were there before. And then, once you copy the object over, you go along and inspect, or you scan the object. And, of course, the language runtime knows exactly, what type the object is and knows where the pointers are. And just looks at these pointers and says, like, okay, maybe, I should copy some more pointers over, because those are actually all clearly, part of a live data structure. And so basically, maybe we'll take the top level pointer, look at that object, copy that object over, to the to space, update, the pointer here, to actually indicate that actually, it has been pointing it to the now copied version of the object. And then, of course, just later on, we need to remember that actually this object has been copied. And so we store a little bit of extra information and remember that this object is actually now stored there. And this process, of sort of moving an object from the from space to the to space and leaving a forwarding pointer in the from space is called forwarding. Okay, so we did this, we did fix this pointer, we fixed that pointer. There's one more left. So we'll look up that object and we copy it over like before. And it still has a pointer pointing to this object. So now we look at that particular pointer, look at that pointer, see, that actually has already been copied. And in fact, we know what the new location is. And so we can just straight update it, to point to the right place. Okay, and so at this point, all the pointers have been, correctly updated. The whole structure, the whole cycle basically of objects has been moved from the from space to the to space. And so at this point, we're done. At this point, we're done. We forwarded all the objects, and basically the from space now, all the objects in the from space are being discarded. And it's now free space. Does that make sense? And that's the basic plan in a copy and garbage collector. Okay, now the scheme that actually is used in the paper, has a couple sophistications. So I want to talk about them. The first sophistication is that they're called, this is called Bager's algorithm. It's an old algorithm, and one of the nice features it has is that it's sometimes what it is originally called real time. And real, what it meant is it's an incremental garbage collector. So, and the main idea is that here, if we have our to, from space and through space, the main idea is that we have our root again. Here's our root. It had 2 pointers, and it's pointing back. The main idea is that it's not really necessary to stop the world and copy everything over and then basically resume computation. The only thing really necessary is to actually move copy over the root and basically do nothing else. And so basically, at this point, the root has been copied, but its pointers are still pointing here because that object has not been scanned. It hasn't been, its pointers haven't been updated yet. And the basic idea is then whenever the application calls new, on every new call, you scan a few more objects, or you forward a couple more objects. And that's sort of nice, correct? Because basically you spread, the cost of actually, copying the complete, active or live heap from the application in incremental steps. Every call allocates, contributes a little bit, to actually the complete copy operation. Now, of course, the application might also be using, some of these pointers. For example, if the root will be dereferencing, like say this second red pointer, it's still actually pointing into the from space. And of course, that is dangerous because we shouldn't be tracking pointers in the from space. And so basically, this means that like every time you dereference a pointer, you need to check if it's in the from space, if in from space. And if so, do the forwarding. And so the application is allowed to use like the pointers, but basically the compiler has to instrument the application that basically every pointer access is sort of surrounded by that check, so that we basically maintain the invariant that all that any pointer in the to space points to objects in the to space. And we need to ensure that's correct, because when we in the end we're done, we want to remove the from space and have so that we can discard it and reuse it as free space. Okay, any questions about this? This is sort of the basic setup. Okay, so now, if there are no questions, the paper makes 2 points, about this scheme. One is, it's annoying or too bad that you actually have to do this dereference every time. So basically, this means that what a load or store instruction, instead of being single instruction, it actually is a bunch of instructions, namely a branch instruction and perhaps in calling a function to actually do the forwarding. And so that increases the cost of the application. And the second thing that it actually sort of points out is that it is not that easy to parallelize the garbage collector, because like maybe in a nice setting, it's like if you're running in a multi-core machine where you have a lot of free CPUs, basically, really nice if the collector, just could in the background, traverse the object graph and copy things incrementally over as it continues. But if the application at the same time, is using the graph there's a risk, that the application maybe, there's one of the reference check, one of these checks, and starts copying an object, while at the same time the collector is also copying the object, and we're not very carefully, we may end up with the object copied twice and the pointers not pointing in the right places. You can easily see, correct, that there is a race condition, a possibility of a race condition. And so the paper basically describes the scheme, and it says like, if you had these user level primitives, then actually you could do something different. You could do a cool trick, and you can actually use VM, virtual memory, to basically reduce the cost of the check and almost get concurrency for free. And so the basic idea is as follows. We have our same setup, our from, and here's our to, and what we're going to do is like we're going to have a region. We can actually divide the to space sort of virtually, or not literally, but we divide the to space in an area that is unscanned. So let me be a little bit more clear. We have an area basically of the area that is scanned, and then there's an area that's unscanned. And initially, basically, the whole area is unscanned. So when you start out, you make the flip from the from to the to space. Nothing has been scanned yet because there's no objects yet in it. And so, but then basically the scheme starts in the same way. We copy over the root object. It used to be there. We copy it over. It has some pointers. Basically these pointers point still back into the and these pointers point back into the old from space, and so that's it. And now we're basically saying, and what we're going to do is for the unscanned area, which is at this point everything, we're going to just basically map them with no permission, map them none. And so what does that mean? Well, that means that if the first time around the application, after we did the flip, the garbage collector did the flip, the first time the application uses the root pointer, it will get a page fault, right? Because that part of the address range is actually unmapped. And so basically then the idea is in the fault handler, scan one page of objects, and forward the ones that need to be forwarded. And so basically, we, in this particular setting where we're only copied over just the root so far, we have, we're going to just copy over the root. We're going to scan, the pointers in the object to which the root is pointing. In this case, there are only two of them. We kind of copy over those two objects, into the unscanned space, or maybe let me draw them slightly different here. Just make it look like we copy over those two objects that we're pointing to, and basically we update, we move the scan line, from here to there. So this is now scanned. And so after we scan the page, we can actually increase, basically protect or basically unprotect. You can unprotect the page, unprotect the scan page. Okay, and and then the application can just now access the particular object because we translated the pointers inside of the object, so it's safe to expose it to the application. The application can traverse those pointers. Of course, if those pointers are still pointing to objects that haven't been scanned, then we'll get a page fault again, and then we scan a little bit more. And so it basically has the benefits. It's still incremental. We can still do a little bit of work, every time. We can also do it every time on a new. We can actually allocate, do some work. But it has the additional benefit. There's no pointer check anymore. Or the pointer check is still there, but it's done in hardware. The VM hardware does it for us. Does that make sense? Any questions about this plan?
I have a question.
Yeah.
So in the handler, you're saying that you scan one page of objects, but
Mhm.
how do you know that the objects that the root has references to will fall into the same, like, how do you know that the objects that really need to be forwarded in order to not violate the invariant will be in the same page?
You'll be okay. There's some set of objects in the page. You start. Okay. Let's say you know what the. Okay. At the beginning, when we flip the spaces, there's nothing in the two space. What we could do is, like, what the runtime could do is just copy. I described it as copying one page, but basically to copy over or forward one page, you know, basically copy n objects over so that they fill a complete page. Right?
I see.
So now we have n objects sitting on that one page, all unscanned. Then at some point the page fault handler will happen, and then, you know, the garbage collector, the collector, you know, goes through each object on that one page and looks, you know, for its pointers. And for its pointers, it copies over those, you know, objects into the unscanned part of the two space. And so that if, you know, anybody or if the application ever would use one of those unscanned objects, will get a page fault and then can scan those, et cetera, et cetera. Does that answer the question?
Yeah.
Good. Okay.
Oh,
Any other
sorry,
questions?
I also had a question.
Yeah.
Yeah. So after you do this, do you flip the to and the from,
Yeah.
or okay?
Yeah,
Thank
so
you.
you start out in the from space, you fill it up, you flip to the, you go copy it over to the to space, and then you call the from. Once you're done with completely with scanning, and you're done with the from space is completely clear, you flip the names and you start using the to space to actually do the allocations until it's full, and then you flip again.
Thank you.
Any further questions? So one of the things that one of the arguments the paper also makes is that, you know, the one other thing that the VM system or using VM simplifies is basically concurrency. And the argument is that basically the collector, you know, can just go through the unscanned pages. So we have, we can go through the unscanned pages and basically scan one page, you know, at a time. And if it is guaranteed that the application has no pointers or cannot access in the same time that page because it's unmapped. And so, you know, as long as the paging hardware basically sort of introduces, you know, sort of an explicit synchronization or protection against races, because only the collector can access that page, and the from and the application can actually not access the page. So it gives sort of a nice automatic sort of parallelism where the application can run and do its business, the collector can do its business, and they will never step on each other's toes, because if the application ever will touch an unscanned page, it will get a page fault, and the collector never touches scanned pages, and so it will never interfere with the application. So you get sort of concurrency for free, but it actually has a tricky issue. So although it's almost for free, you know, there's actually one thing you actually have to arrange, which is the area, correct, in the unscanned area was actually unmapped. So if we look at our picture from before, here's our, you know, to, or here's our from, here's our to, and, you know, we have, you know, that sort of split in the unscanned and scanned area, and unscanned, it has no, you know, there's none, protected none. So that raises the question, you know, how does actually the collector, go through it because you can't actually access those pages because they're unmapped, correct? Or the protected with they're inaccessible. And so the trick is basically as follows, and this is where map 2 comes in. What we're going to do is actually we're going to map that same physical memory. We mapped it once, correct? We mapped it once in this way. And we're going to map it in a second time in the collector's view, sort of the collector's view of the 2 space. So here's the collector's view, here's the app view. And in the collector's view, where I still have to and from, exactly like before. Oops, I didn't try. We have to and from. And what we're doing actually, here's our unscanned area. But in the collector, we map actually the unscanned area read and write. And so that the collector actually can go through, look at the scan the objects, and forward pointers as necessary. And so this is like at the place where this map 2 call is necessary, where a range, a piece of physical memory is actually mapped twice in the address space of an application, one at 2 different levels of protection, to basically make the scenario like this work. Any questions about this?
I have a question.
Yeah.
Do you kind of give each, like the collector and the app, different versions of the page table, or?
No, they have the same page table, correct? But they have the memory mapped in 2 places, the physical memory mapped in 2 different places in the address space, in 2 different places in the page table. And in one place, you make basically the mapping is invalid. And in the other address range, you make the mapping read-write.
Okay.
Just make this a little bit more clear, since there were so many questions about it. I sort of have a trivial implementation of actually this basic ID, the ID that was described in the paper, and just to make it a little bit more concrete. And so let me walk through this and ask, feel free to jump in. This is basically a toy implementation of what is described in the paper. And I'm sure it has bugs. I mean, I haven't really tested this in any way seriously, and it's mostly there to just illustrate, to make everything slightly more concrete. So the collector, the API, if you will, that the application uses is a new and read pointer. And read pointer is that basically does the check whether the pointer's in the from space, and if it's in the from space, then it needs to be copied. And of course, when we're using VM tricks, then basically this read pointer is going to be very cheap. It's going to basically return return this argument. And just for the simple application, I have a linked list, and it has 2 roots, pointing one to the head and one to the last node of the linked list. It's a circular linked list, and nothing really too exciting going on. Basically, what the application thread does is it, 1,000 times makes the list and makes a list, and then checks the list. And so it generates a lot of garbage. Like every time after the make list is done, it's going to make a new one. And so the last list is basically garbage. And so the collector actually has something to do. And the make list, is basically a little bit of ugly code, mostly because, every pointer needs to be wrapped in this read pointer check. Right? So normally, of course, this would be generated by a compiler, but I don't really have a compiler for a garbage collected language. And so I'm just simulating what maybe a compiler might have generated. And basically what the code does is, it goes through it builds a list of at least list size, allocates a new element, and sticks it, prepends it at the beginning of the list, and then updates the last pointer to point basically to the beginning of the list. So that's circular. Any questions about this little fragment of code? So the most interesting question, of course, is like what goes on exactly in the collector. And let's first look at the case where there's no virtual memory, where we're not using these tricks. And so we just have to look at 2 APIs. One is new and read pointer. So use new, and forget the mutexes, that is for the VM-based solution. And basically what, and forget that we're, assume that we're actually not scanning, we're not collecting for a while. We're basically, we check if there's enough space left in free space. If there's enough in a free space left, we just bump up the pointer a little bit, to allocate that object and return it. And if there's not enough space left, then we basically have to flip. We have to do a garbage collection run. And so, look at flip. Flip basically switches the to and from pointers around, and then basically forward, the two routes that this application has, to from the from space to the to space. So let's look at forward. So here's forward. It looks if the, forwarding the object that is pointed to by O, it looks if O is actually in the from space. If it is in the from space and it has not been copied before, then we're going to copy it, and then we're done. So we moved the object from the from space to the to space. If we already copied it, then basically we can replace the pointer, with the new pointer is actually the pointer to the already moved object, and we return that. Okay, so that's forwarding. And so then read pointer, we actually have a read pointer basically goes through. Oops. Let's see what the read pointer, what the garbage collector does with read pointer. It's like right here. If we're not using VM, basically what it does a forward operation, and the forward operation is checking if it's in the from space. If it's not in the from space, then do nothing. If it is in the from space, then do this copy again. And so here we see this as sort of the expensive check is really checking if the object actually sits in the from space. Any questions before I jump into sort of the version that actually uses the VM tricks? Okay, let's look at actually what the VM tricks. So the setup is a little bit is here. Basically, there's a call called shared mem open that allows you to create a shared memory object. It's a Linux call or a Unix call, and it just almost behaves like a file, but it's not. It behaves like a file, but it is not a file. It just sits in memory. There's no disk space associated with it or anything. It's like an in-memory file system, if you will. And basically, what we're doing is we allocate one of these shared memory objects. We truncate the shared memory object to be the size of the sum of the to and the from space. So we have a space, and then we map it once for the mutator, and we map it once for the collector. And so this is basically these sort of sequence of operations here. The share mem open, the truncate, and the to m maps are basically sort of the equivalent of the map to calls. And so when we look at let's go back up to our implementation. The read pointer in the VM case does nothing. There's no check whatsoever. We just return the pointer straight. And then, of course, if we use the pointer, we're going to get a page fault, like as before in the SIG-roots table application. And here's the page fault handler. So if it's a page on an, actually, I'm running a little bit ahead here. If the object was moved somewhere earlier and is sitting in the unscanned area, we're getting a page fault, and basically the scan page function runs. But the scan page function runs actually with the address ranges of the collector, and so it actually can work, because otherwise the mutator the application cannot touch those pages, because that would take a result in a page fault. And once we've unscanned, once we have scanned all the pages, then the collector actually makes the page actually accessible to the user application. It may be helpful to look at flip again, just to see what happens. Okay, so at flip, what happens, we switch from so the front space is full. We basically mark the whole to space as non-accessible, to the application. And then we the collector moves actually the root head and the root last, to the to space that the application cannot access, or at least not directly. And, that will result whenever the application accesses root head or root last, it will actually result in a page fault. And then the collector can copy things over and then unprotect the one page. Does that make sense? Okay, note in the handler, correct, that is actually crucial that first the page is scanned before, you make, the page accessible to the application, because if you were to make it accessible before you scanned it, and if there were multiple application threads, then those applications might be looking at, objects in the unscanned area. And of course, that we need to forbid that. And so this code basically first scans and then raises the protection level so that the application can access the pages. Any questions about the collector and the tricks to use virtual memory? Okay. Well, in that case, I want to wrap up, and a couple points I want to make, or one point basically, before wrapping up. One question to ask, should you use VM for this? And really is, does these tricks pay off? And because many of the, for example, the garbage collectors, and there are many garbage collectors out there that actually don't use virtual memory at all, but use basically instrument, the compiler is actually very aware of the code generated and instrument, the code correctly, and has all kinds of other tricks to reduce, the performance overhead. So, the observation is that in most cases, it can be, most cases could have been implemented with extra instructions. And that is, if you're basically, if it's a compiler or a runtime or for a programming language, then maybe that's not so bad, because the compiler can do the instrumentation. But if there's not a runtime application, it's not a compiler application or a programming language sort of setting, then that might be painful. And so it turns out that for some of these applications where like there's no compiler involved at all, for example, like checkpointing or the shared virtual memory, those actually really need these kind of primitives. And so in practice, it is the case that enough application programmers have find these primitives worthwhile that basically today's operating systems support them. Okay. Some people ask, or a lot of people actually ask, what has changed, since what's it changed since 91? One thing that actually changed, of course, like most Unixes do support the primitives now, and in fact there are many changes since 91. Maybe hard to imagine, but basically there's a continuous development in the VM system. So if you look at like the Linux Git log, you'll see there's there's continuous development of all aspects of the kernel, but including continuous development of the VM system. And some of the bigger changes, what are some big changes in the last whatever N years? There's now a 5-level page table to deal with really large bigger addresses. There's address space identifiers to deal with TLB, the cost of TLB flushes. More recently, a year ago or something like that, something was introduced is called KPTI, kernel page table isolation, which is there because of the meltdown attacks, and which we'll talk about later in the semester. So it's the virtual memory system is absolutely not a static system. Almost absolutely no aspect of any kernel of the Linux kernel is static. There's a dramatic amount of changes, like almost every couple months, in different aspects of the kernel. And so, and systems once in a while actually completely rewritten. So it's always in flux. Okay, let me stop with that. And if anybody has more questions, please feel free to ask them, or if you have to go, feel free to go.
Could I ask about one of the first slides
Yeah.
where, sorry, I'm trying to see it. It's VM implementation, like 2 slides after this one.
Yep.
Yes, that one. What do you mean exactly by contiguous range of addresses? What are your?
Yeah, a continuous range of virtual addresses. So if a VMA, the VMA covers a range, say, from 1,000 to 2,000. And if you had another address range, like 2,100 or something like that, that would has its own VMA. So every VMA covers a continuous range of addresses. So no holes in it.
Okay.
And it makes it easier, as you will see in the MAP lab, that will make it much easier to reason about things. Because
Okay,
you
I
can
see. So
that any
each of
address in
those.
the range of the VMA has no hole in it.
Okay. Okay. So those are for this particular use case for mmap, I guess, right?
Yeah, for MAP, yeah.
Okay, I see. Thank you.
So basically, you can think about it like for every mmap call, there's one VMA if the mmaps don't overlap.
Oh, okay. Okay, I think I understand. Thank you.
You're welcome.
To ask, so for the to and from garbage collection, when do you stop and start again? Like I guess collector runs can run all the time if it's concurrent.
Yeah, that's like one of the cool things about this the VM solution. The collector can just run all the time, and it can stop once basically it has there's no more unscanned objects.
Okay, so you have to go through. That means you. So you'll go through all of the stuff, like all of the objects in the from section, and you're either like gonna collect them or copy them over. How do you know you've gone through all of them?
At some point, you trace the object graph down, correct? And
Okay.
at some point, you're not adding any objects anymore because you already copied them in the past.
Okay, that makes sense. Yeah.
If you don't add anymore, basically your unscanned area is not growing. So if your unscanned area is not growing anymore, you're done.
Okay. And then when you copy it over, you unmap it. So if someone tries to access the old pointer, it's going to be invalid.
Yeah.
Right. Okay, that makes sense. Thanks. All right, I'll see you guys later.
Yep. You too.
Thank you.
You're welcome. Okay, I think that may be it for today.